So today we're going to be talking about human body vibration, specifically the effects that vibration can have on our body, some of the regulations that are out there that basically work towards preventing the health concerns that can come from high levels for long periods of time. We'll also look specifically at just two standards, one related to hand-arm vibration and one related to whole body vibration. There are many ISO standards related to this human body vibration field. And thankfully, we have all these standards because they're very detailed and useful for doing this type of work. So why don't we get started first and just talk about the vibration that we might be experiencing. As you can see, a power tool, we would probably imagine that that would induce high levels of vibration in a person's hand or arm as they use that tool. As well, maybe the same thing for someone who works as an auto mechanic or something, using a pneumatic impact there. Even in dentistry, there can be some high levels or long exposure because of dental drills, a lot of cavities out there that dentists need to fix. Then on a different level, from a whole body perspective, there can be vibration from ships, airplanes, helicopters, an example of some mining equipment. So vibration is everywhere, kind of like the slide says, and it can be introduced into our body through a variety of tools, as well as whole body vibration from a variety of different ways in the transportation setting. So we could probably break human body vibration down into maybe two categories: whole body vibration and hand-arm vibration. And it may seem strange, I guess, to say whole body vibration is a different category from hand-arm vibration, because most of the time when people say the whole body, they assume the hand and arm are included. But from the standpoint of these standards, hand-arm vibration is considered separately from whole body vibration. However, if we're talking about human body vibration, then that would mean we're taking into account the vibration from whole body as well as hand-arm. And a scenario might be something like this, where you see this guy using some type of power tool to break up pavement. And obviously his hand and arms are going to experience some vibration, but maybe you've probably seen it sometimes in the videos or movies rather. They show a construction worker who may have a larger belly, and you'll kind of see it kind of drooped over a jackhammer like this. And that would probably be a situation where the whole body as well as the hand arm are exposed to high vibration levels, and it could be for a long period of time.
So like a whole body, it's like your spine and everything that could be affected, your legs, whereas hand arm is really like where you're gripping.
That's exactly it. That's exactly it. Too, with regard to the effects of vibration, it can also be that we are just talking about vibration that kind of falls into the area of comfort or discomfort, or how our product is perceived because of the levels of vibration produced in it. So we might say, well, one product seems to be of higher quality because the vibration levels are lower. And it might even play into whether or not we purchase one product over the next. Those type of human vibrations, we're talking comfort, perception, quality, just comfort or discomfort. However, what we're really probably focused on more often than not is the safety and health aspects that can come from high vibration levels over a long period of time. From a safety standpoint, it can lead to fatigue, reduced concentration, that could, increase accidents. Then from, even very serious health concerns, lower back pain, something called white finger syndrome. It's also, I guess, referred to as HAVS, or hand and arm vibration syndrome, or Raynaud's syndrome, if you kind of look it up on the internet. And you see an example here in the lower left, what can happen to someone's hands if they kind of exposed to high levels of vibration, excessive levels of vibration for a long period of time. And some of the symptoms would be like cold fingers or tingling or numbness. And then like severe cases, it can lead to this whitening of the fingers. You can kind of see on the right hand there. And it even can be permanent, the damage caused by these excessive levels of hand vibration. So it's a serious thing manufacturers try to prevent, and hence why regulation has come along to try to protect the worker. And then even from the whole body vibration standpoint, it looks like an icy hot commercial, but there could be, serious back pain that can be a result of excessive levels of whole body vibration. Maybe if you have to ride around a quarry all day over a very rough terrain, and it's not very good isolation in the seat, perhaps, or something. Those are kind of the two domains when we're talking about this human vibration: comfort and perception, but also this health and safety. That's kind of why the European Union, they realized and decided they needed to take the lead to create this human vibration directive to kind of address these concerns. And this directive applies to anyone who wants to sell products on the European market, actually. The directive poses a maximum limit on the daily exposure to vibrations. So if you don't comply with these limits, then you can't sell your product or your equipment in the European market. So there's a lot of pressure on manufacturers to make sure that the vibration levels of their tools are as low as possible so that they can not only have a competitive advantage, but it's also good for the end user, the worker. And that's actually, from an employer standpoint, who has to protect his employees, that's helpful for them, because if those daily vibration exposure limits are lower, then they can utilize the equipment for a longer period of time without violating any legal limits. So they can be more effective, efficient, and do more work. Here's some of the ISO standards that are related to this vibration directive. Now, the vibration directive defines the limits, but it refers to these following ISO standards to determine how the vibrations are measured. So there's the ISO 2631-1 that defines basically the specific sensitivity filters. They're used to express the effect of vibration on humans, and we'll get into that a little bit more a few slides later. There's also ISO 5349, explains how we apply filters for the measurements of hand and arm vibration. And then there's very specific, tool-specific, I should say, ISO standards, like the 8662, that kind of give further detail on how different types of hand tools should be tested to understand the vibration that they cause.
So something like 5349 tells you how to take the accelerometer and apply a weighting to take into account the effect on the human hand. But
Right.
Depending on the tool you have, you might have to measure in specific places and run the tool a certain way. So that's what those tool-specific standards do.
Exactly.
I see.
And then, as you see at the bottom there, the whole body vibration, there's different domains, whether we're talking about vibration in buildings, vibration in transport, there's different ISO standards. This is the typical setup, maybe, how we would measure, for example, hand-arm vibration for a drill in this case. So in practice, this measurement is done in 3 directions. At the position where you would hold the tool, right? Maybe we call it the grip portion. So that means, like, you could have a tool that has a single hand grip, or some tools they're designed to have 2 grip positions. So you would measure simultaneously at both of these locations. And we're going to measure in 3 directions, X, Y, and Z. Once we gather our acceleration data, this time history data, we're going to apply a weighting. And the reason we're going to apply the weighting is because if you think about the human body, different parts of our body are sensitive to different frequencies. We can kind of think of it as a system, spring mass dampers. And if you're talking about a chest, there's going to be certain frequencies where your chest is more sensitive to vibration versus your legs, for example. Even whether or not your leg is flexing or if it's in a rigid position could have an influence on the sensitivity to certain frequency ranges. So because of that sensitivity, we apply this hand-arm weighting when we're doing a hand-arm vibration exposure measurement per the 5349. If you take a look at that ISO standards, you'll see a particular weighting curve in there and how to apply it. But as we look at this weighting curve, we can kind of see what I was talking about, where maybe the lower frequencies and the very higher ones on this frequency band are not emphasized as much, but rather in this region here, 9 to 20 some hertz are more emphasized for this hand-arm vibration measurement. So we're going to apply that weighting to our time histories. And after we apply that weighting, we're going to calculate using a vector sum from the acceleration that we're measuring in all three directions, an overall or a total RMS weighted vibration level. And once we get that vibration level, we can compare it to levels that are stated in the ISO standard, in this case, the 5349. And you'll see that there are two different levels that we would be paying attention to. There's the EAV, the exposure action value, which says is 2.5 meters per second squared. So if we are below this, then we don't have an issue. We can continue using the tool. But if we were above this, let's say 6 meters per second squared, we could see that number one, if it's between 2.5 and 5, we should be taking action to reduce the vibration level. But once we cross 5 meters per second squared, we have to immediately stop use of that tool because it's unsafe and dangerous. It can lead to some of the health risks that I mentioned earlier, kind of that Raynaud syndrome or that white finger syndrome as an example of possible health risk. And this is pretty straightforward to apply, actually, so I thought I wanted to do an example. Okay, let me hop over to TestLab, and maybe we can just step through a simple example. First thing you want to do is turn on your add-ins, and there is a human body vibration add-in you want to turn on. And it's only 6 tokens, so that's a good value. And this is going to give us access to these filters that we can utilize for weighting our time history data, both for the ISO 2631 and for the 5349. So we already have that on. So I have some time history data here, and we can just take a look at it. And this is from a Tri-X, and we're just, in this case, it's just one handle position. And you see that we measured vibration in the X, Y, and Z. So what we'll do is take that time history data, we'll put it in our input basket. First thing we're going to do is go to time data selection, and we need to bring it in. So we'll hit replace. So we can kind of see our time histories here. Under view them, we just click on this green box here. And we need to now do the weighting. So we can go down here to our time signal calculator. We can choose insert function. And if you go down to conditioning, you can see you can kind of just shorten the list. If you get all, it's like, you just got to scroll down further. I'm a little lazy. So I can go into groups and go conditioning. And I see the one that I want right here, ISO 5349. Hit OK. And like we said, we're going to use this same filter for all 3 directions. So I'll just type in the function there, C14, hit OK, and do it again. Hit OK, and the next one would be C15. Now, if you really wanted to make your life easier, I guess you could just copy this, go here and paste it using Control V and type in the 16 as well. So we'll go ahead and calculate, and we can see if we wanted to compare these. You can kind of see just looking at it from comparison to the non-filtered. And we can take a look at it inside the navigator as well, but clear that it reduced some of the frequency content in there. So let's go save as, and I don't know, we'll just call it arm hand W for weighted. Hit OK.
Now that saved all 6, didn't it?
It did. And that was just because I was going to
So we know 17, 18, and 19 are weighted, huh?
yes.
I'm double tracking you, Charles.
No, I appreciate it.
Oh yeah, that amplitude's reduced, huh?
Yep.
Or
So
properly weighted.
Yeah, properly weighted per our ISO standard. So what we'll do is replace those in our input basket. Go back to our time and data selection, hit replace. And now what we want to go over to is time data processing. And we'll select all 3. And if you go under section, there's going to be a tab called level calculation. And this is where we want to go to. And we'll go down here and we'll select RMS, hit add, and make sure you have the right group selected, in this case vibration, makes sense for us. Hit OK, and we will calculate it. And if we go back to Navigator, and this was the processing name, go to sections, and you'll see that you actually get two RMSs calculated. One is RMS lowercase t, and then there's RMS cap t. And the one we're interested in, number one, I'll tell you, is the RMS cap t. But the difference is the RMS lowercase t is the RMS between the current tracking point and the previous, whereas RMS cap t, and this is all in the help, so if you want to look it up, RMS cap t is between RMS at the current point and the initial. So this is the one we're interested in. And just so we can, I'll throw a front back up here. You can take a look at it.
You have a little t in there and a uppercase T.
I do. I did not want that one. Thank you.
So this is like a sort of an accumulated, huh? Although there's like some exponential averaging. Cap T.
Yes, that's the one we're interested in. And we can kind of see the comparison between vibration levels in the X direction and what was specified as the Y direction in comparison to the. So if we go over to data block processing, and if we just make sure we have the right one selected, and our run, hit OK, hit replace. There we go. Now we need to do that calculation, right? Where we were squaring it and adding them and taking the square root. So we look over here, it's F4, F5, and F6, right? We want the RMS cap T. And what I wanted to show you was that you can save these formulas and just not have to type this in every time, obviously. I saved one from a different test, I guess, I was doing, but nonetheless, it's very easy with this particular test. And we'll call this not steering, but maybe drill.
It's the grip of a drill or something.
Yeah, exactly.
All right.
And we're going to save it into the hand-arm section. Hand-arm section inside our processing, and we will call this 5349. Maybe I'll go -2 in case I have another one already. And we'll hit calculate. Go to Navigator. And now you'll get this user metrics folder that wasn't here before. And you can see the folder that I created, the ISO 5349 and our drill.
All right. Did we pass?
We did. In fact, we're interested in the last value. So what we could do is go to options, calculate it, value, and say last. And we'll call that HAV and put the unit on it.
0.92.
0.92. So if we go back to the slide here, we don't have a problem yet. We don't need to take any action. Everybody can continue to work. So, okay, that was just a straightforward example. Hopefully I wanted to show you how to do it inside of TestLab.
I noticed something back in the software, and because you went through a lot of steps there, right?
Yeah.
I noticed like in data block processing, for example, there's a little checkbox there, calculate automatically.
Yeah.
And so if that's on, and then like the previous step you did was time data processing where you calculated the RMSs, is there a calculate automatically there too in time data processing? Calculate after each. I think that's sensitive if you're in an acquisition package.
Right.
And then same thing in time data selection. Is there a calculate automatically?
Yep.
Yeah. Again, it's sensitive if you're in the acquisition. So the idea is you could set this up so that you do the measurement and then all three of these steps are done automatically. You wouldn't have to do them manually. Is that right?
That sounds like something that I would definitely be a big fan of.
Yeah. Well, good thing I mentioned it for the recording so that somebody who's setting this up, once they've set it up once, if they turn on that calculate automatically, then life can be good, right? It'll just apply the
Absolutely.
filters in that first step, calculate your RMS in the second, and then calculate the vector sum in the third.
And I
All
guess too,
right.
with regard to the formulas, you don't have to use channel ID. So in case you're not using channel 14 or something on your front end, you could write vibration in the X or vibration in the Y so that it would always find it and do the calculation. Another example, just quickly wanted to walk through, was whole body vibration. That's the ISO 2631 that's references to. And because we're talking about a whole body vibration, you might remember, right? We won't be including hands. That would be human body vibration. So just trying to drive home that point that the whole body vibration doesn't consider hand to arm vibration. That's human body vibration we would be considering. So the vibration maybe of the driver of the experience on the steering wheel into his hands and arms wouldn't be considered if we're just doing whole body vibration. But we would have typically an accelerometer, triax at the feet, one at the seat back, one on the seat surface. I don't know if you've ever seen one of these, but it's basically a triax accelerometer built into this rubber pad, measures X, Y, and Z. And this would be a typical setup. And the typical process would be similar to what we did for the hand-arm vibration. We're going to apply some weighting filters, but then there's another step where we calculate the crest factor and something called the MTVV, what's maximum transient vibration value. And the reason we're doing these calculations is to help us decide which method we would use to calculate the vibration level, be it this VDV, which we're going to talk about, vibration dose value, or this running RMS, kind of a moving average. Really wanted to highlight something brought up earlier. When we were talking about hand-arm vibration, there was only one weighting filter that we use for all directions. However, when we're talking about whole body, there are different weighting filters that we use per direction. So as you can see, for example, for the seated surface, once it gets back here in a second, it's WK, WD, WD. For seat back, it's WC and WD. So have to be cognizant of that fact when you're filtering your data. If you're talking about the seat back or the seat, we need to be using the right filters per the direction that acceleration is being measured in. This is just some more examples of the filters that we'd be using, and wanted to highlight this point that it even makes a difference whether we're talking about the position of the person, if they're standing, seated, or lying on their back. That would play into the role of which filters we would be using, which weightings we would be using. Like, for example, this recumbent seat back would be for someone lying on their back, basically. So yeah, these weighting functions, just to drive home the point, again, we're applying to the raw time signals before we perform our calculations. And it's based on the position or the posture of the body, as which ones we're going to be choosing. Second step in the process would be, like I said, we're going to determine the crest factor, which is just basically taking the peak and dividing it by the RMS. Inside a test lab, you can do, using time signal calculator area, single value statistics, so we can easily calculate the crest factor for our data for the different degrees of freedom we're measuring. So that's not a problem. I'll show you how we do that. And with that crest factor, what it's telling us is if we, for example, have a crest factor of 9, which wasn't the case in this particular example, that would, according to the standard, tell us that we should use the VDV method for calculating our vibration exposure levels. Now, there are 3 different methods, basically, user approaches we could use for calculating this vibration exposure values when we're doing this whole body vibration. It could be just calculating the root mean squared, or it could be the running RMS. It's kind of a moving average, time step of 1 second. And typically we're going to choose root mean squared if we're dealing with a vibration that's kind of continuous. It doesn't have any transient or impulsive shocks in it, for example. If it's one that is maybe still very continuous, but still has some amount, small amount, I would say maybe, of impulsive or shock events, then we would probably lean towards using running RMS. Another thing stated in the ISO standard in great detail, I'm just giving you kind of a high level, trying to condense it to a small, short webinar. But we need to take into effect the adjustments we need to make on each axis for the K factor and the exposure time. The K factor is whether we're talking about we're doing something to examine the health effects, or is it just more related to comfort and perception, as well as the exposure time, how long the tool's being used needs to be calculated and factored into as well to scale these vibration levels. The VDD, vibration dose value, would be one that we would use if there's a tool that has pretty much is very dominated by impulsive shock events, not just kind of a continuous stationary type signal. That would be very obvious if you look at the crest factor and it's like way above 9. Then if you look at the standard, it will suggest that you use the VDV. However, too, I guess I should bring up this MTVV that's calculated from the running RMS. If you do that calculation, and TestLab does all these calculations for us, so it's very handy. Within the standard, it points out that looking at this maximum transient vibration value, there are calculations you can do with it to determine if you should not only look at running RMS, but also VDD at the same time should be considered, which is stated in the ISO standard. So if you do use running RMS, you want to do this MTVV calculation to be sure that whether or not you should also consider doing a VDV calculation. And same thing, we need to scale it for the proper K factor, whether it's for health or comfort and perception, as well as with regard to exposure time. I think what I wanted to do now is kind of walk you through an example in TestLab, whole body vibration. And we'll just start off. I probably won't do any of the calculations just because there's a little more involved and we're getting near the end here. Involved in the sense of having to type them in one time. After that, they can be saved and it's been showed automatically calculated. So this is just from the seat surface, comparing the weighted to the non-weighted acceleration values. Like we said, that's the first step before we do any calculations. We have to utilize the correct weighting depending on the location and the position, direction that we're measuring. So now all of that is stated within the ISO standard. Once we import our data into the time data selection, we would just use the proper filter. And once we have the filter data, we could go over to our time data processing. Same thing, we would go to level calculation. We could calculate the VDD. That'll be in the drop-down list, as well as the running RMS. One thing I did want to do is show you, place an input basket, the calculations that you can do. Statistic, single value statistic. So maybe you don't even know about this, but there's an additional hidden panel here for single value statistics. If we select that, and you can choose which functions that you would like to display here, statistical functions. You can hit calculate, and then you can see the crest value, which is pretty high, 26, 21, 22. In fact, there's only one, or no, there's two, three below 9. So definitely this is one where we'd want to do a VDV calculation based on the ISO standard when we look at the crest factor. I'll show you here. Once we have our level calculations for pedal, seat back, got the running RMS we calculated. Same thing, pedal, seat back, seat surface for VDE. Once we have all of those, we can go to the data block processing. And from there, we're just doing our vector sums here. And once we have our vector sums, we can look at the VDV pedal total for all 3 directions, as well as seat back. And, oh, this is pedal. This is seat surface, and this is seat back. That seems to be dominant. If we go to running RMS, we can see the vector sums for those as well. But based off that crest factor, we know we probably wanted to go with the VDV total. And doing the calculation across all the axes, we can get the total VDV. And I'm interested in the last value. Again, I can just right click on the legend and go to last value. As well, I should say too, if you wanted to calculate for your running RMS, that MTVV, it's also a calculated content value. It's the maximum. Hit apply. And we should probably change this units because everything in the standards in meters per second squared, not G. So this is how you could calculate the MTVV. And within the standard, it'll tell you other calculations you can do with this to see if maybe you should not be ignoring the VDV, but also considering it. And these would be, according to the ISO standard, the values that we would be comparing to. As you saw, maybe I'll highlight it again. Our VDV total was 14.33. So we're utilizing the VDV. We see that probably we should take some action to reduce the vibration level because we're above this 9.1. We're not at the point where we have to stop immediately, thankfully, but we need to take some actions to reduce the vibration. And that could be with regard to exposure time. Maybe the worker could utilize whatever vehicle, maybe for example, in this case, less during the day versus another one, rotating them, or we just may have to reduce the source levels with more isolation or something like that. Maybe we need to buy a product that has less vibration, high vibration. So if you were utilizing the running RMS, these would be the values for as far as limits that we would use. I think that was really all I wanted to highlight today with regard to how we can utilize TestLab to do these human body vibration.